So in this video, we'll be talking about the concept of deconvolution, which is the process by which you can sort of undo any deformities caused by atmospheric turbulence or imperfections in your optics and try and arrive at a more realistic version of the photons that have arrived at Earth from your object. And this is a process that has to be done very early on while your image is still in the linear regime, which is why you can see our data set here is not stretched yet, but a quick screen stretch will show that we're working on M1, the Crab Nebula. Now, this is done on your luminance image. If you do one-shot color with DSLRs and your processing workflow doesn't involve extracting luminances, you can still do it on the color image. If it does, if you do work in different filters, you do want to do this on your luminance. And this has to be done before really anything else. And the reason for that is we're going to be making use of something called a point spread function, which is actually a tool that we're going to be using. And what a point spread function is basically, you know, you see all these stars here and they're rather large on the image, but really they're very tiny point sources. The size of this star over here might be or would be less than 1 pixel at this resolution. You know, so why is it several pixels wide? Well, it turns out there's a very well-defined way that point sources will show up on an image sensor. And it spreads out over an area, and that area obeys the point spread function. And this, I pulled this off Wikipedia. This is what a perfect point spread function looks like, with absolutely no deformities or anything. You know, you have the background here is pitch black, and then you have these little waves, and you have this whole thing. And of course, if you're looking from the top down, you see this whole area as the star. This is called an Airy function, and you're never going to see this. You know, the closest you get to this is being in outer space with excellent optics, but it's never perfect. And so what ends up happening is, even though you expect your stars to have this sort of distribution, you end up with stars that have this instead. And this is a real PSF taken from one of these stars in this image. As you can see, you know, it's a lot fatter, the peak is not as well defined, the background is smooth but it's still bumpy, especially over here. This is actually due to a neighboring star. And it looks very different from this. And so what deconvolution is the process of taking something that looks like this and trying to turn it into something like this. Now, the advantage to a PSF is it's the same for all the stars in your image. So the PSF of this star is the same as this, which is the same as this, because the thing that's deforming this disk here is the same atmosphere over a small enough area of sky, the same optics, etc. I mean, they're not physically perfectly identical, but close enough that that this process is useful. So, you know, I'll pull out, this is a different star from the same image. It's a little noisier, a little bumpier because the star wasn't as bright, so the background you can see is a little bumpy there. Same thing here. But, you know, they all have this sort of long slope here, same kind of shape, fat top, stuff like that. And so what ends up happening is, if you can approximate a PSF that is a good representation of any given PSF from a star in your image, and you can run through a process which turns that PSF into, as close as you can, into this, and then you try and run that process on your whole image, you will recover some details that have been blurred out by the atmosphere. Now, to be clear, this is not a method for sharpening, and this is not going to make a bad image look amazing. This is going to be slight differences that you end up seeing, but still important differences, because it's done so early on that when you apply later things like sharpening, you end up enhancing things that have been recovered in the deconvolution process. So what we're going to want to do is we're going to want to start by building a PSF for our image. Now in PixInsight, I'll close this, so I'll show you again. The way you do that is you go to Process, Image, and Dynamic PSF right here. And now what you do is you start clicking on individual stars, and they'll show up here. For example, that one right there. And we've got a star, we've got a bunch of numbers, coordinates, and other things. You don't have to worry about what any of that means. We want to select a lot of stars. We want to select like 20 stars, 25 stars, because we want a good average. But we want to be careful. So if I quickly undo the screen stretch by hitting F12, you'll see that I can't really see the star I've selected, but I can see these here. Now, it's true that the brighter stars have a better signal to noise, which produce a more accurate PSF, but you don't want stars that have been saturated, stars whose center values are the maximum that your image can detect. Because what happens is you get a saturated PSF. And here is what this star looks like. Actually, I don't even think it was this star. If I recall, I think it was this star. So what this star looks like is a PSF. So you can see it's so large, it's huge, it takes up all the same surface area as the other place, but it has got this flat top. And the flat top is really bad because it doesn't really, it loses all the information, it loses all this information here. So if you're trying to turn these into that other image, you're not going to be able to know anything about the top of this while you have the top of this. So you don't want saturated stars. So it's easier with the screen stretch on. You can take it off and turn it on to make sure you're not picking out these really, really bright stars here. By contrast, you don't want to go nuts and hit these dim stars down here because, of course, the low signal to noise PSF looks like this. And I don't remember which star this came from. But, yeah, there's probably a peak in the middle compared to the noise in the background, but look how smooth this is and compare it to this. This is terrible to build a PSF out of. So what we're going to do is we're going to choose stars that are not as big as these and that are relatively isolated from both other stars and from our object. Now the advantage to the PSF fitting is that if you do have kind of another neighboring star or you have a bit of nebula because your nebula takes up the whole image, the background in over a small area is relatively flat, so you don't have to worry about it. I wouldn't choose a star that's on a transition point from a bright part of the nebula to the dark part. But if you have a nebula that takes up your whole image and you hope this swath here is approximately of the same brightness, you can choose stars within that. That's fine. Another good tip is you can turn screen stretch off and on. I find that the best stars are the ones that just show up in the linear regime, but are obviously not saturated like these ones here. And you put the screen stretch back on to make sure you're not picking out ones that are weird transition points, like this one here, this one here. Sorry, not this one here. This one's fine. As you can see, it's surrounded by very smooth areas. However, the Crab Nebula, so these filaments, we want to stay away from. So we'll look down here, there's one. The green box will tell you whether or not, what the area is that it's looking at. So if you're worried about neighboring stars, if the star falls outside of the green box, you don't have to worry about it. Again, the advantage of the PSF is if there is a little bit of overlap or you have a bright star and a tiny, tiny star next to it, as long as you select about 20 stars or so, it will average out things like that. They just appear as bumps in the background noise. And it's a generally good idea to kind of sample stars from all over the image, although if you have, like I do, a central object, you're going to want to sample stars that are relatively near the object or away from the edge where edge effects can occur. Of course, if you have a nebula that takes up your entire image, you're going to want to sample stars from all over the image. So there you can see here's 20. I have about 20. That's fine. We'll go with that. So what I do here is I select all, Control A, and I hit this little picture button here. And this will create, from those 20 stars, a synthetic PSF. This is what the average star in my picture looks like. And we can close this here and keep this. Now, of course, this star is smaller than this one, and it's brighter than this one, etc., etc. But the great thing about a PSF is the brightness and the dimness is really can be fitted to any star, so long as you just match the brightness. It's just the amplitude of that hill. Like this PSF, for example, can be a very dim star or a very bright star. All we have to do is just drag the top up or down and preserve the shape. So PixInsight does that all for you. So you don't have to really worry. You just want a good PSF. So now what we're going to do, we're going to actually look at the deconvolution tool. And we're not going to use it yet, but I just want to show you where this goes. So you go to Process, Deconvolution, and Deconvolution. So you have these different options here: parametric PSF, motion blur PSF, and these are sort of pre-built point spread functions if you don't have your own. And then there's external PSF, which means you've built your own and you're going to tell it what the PSF is. This is the one you always want to be using. So once you've built your PSF, you can go right in here and select the PSF. There it is. Great. Now we have the algorithm. Just leave it as regularized Richardson-Lucy. Richardson-Lucy is a great algorithm for, as I say, trying to reconstruct finer details that have been smoothed out. It's got great success for deep sky images. Iterations we're going to get to. Usually the higher the better, but you do hit a point of diminishing returns. Deconvolution is what's known as an iterative process. So as you go through it again and again and again, it improves because, you know, you're bit by bit you're transforming this into that airy disk. You know, you tuck these in a little bit on one iteration, you make that a bit more of a point on another iteration, etc., etc. Of course, you get to a point where you can't ever actually recover the perfect airy disk, and so the more iterations you go from there on, you're not going to see much difference. And the target is luminance always, even if you're working in a colored image. Now, before we actually perform anything, we need to talk about de-ringing, because what deconvolution is going to do is going to produce a strange artifacts around your stars. So I'll just make a preview, little one over here, and I'm just going to use it, and you can see all this weird crap is happening. Now, this is no good. We don't want this. So you check on de-ringing. Now, global dark will help to get rid of the dark rings around here, and global bright will help to stop bright structures and bright centers of stars from appearing. So if I just check it on and I try it again, now we've got another weird problem. If it looks like this, your global dark is just too bright. These are very fine parameters. You'll never really see them over here. You're always dealing with them very low. So there's global dark at a more reasonable scale. You can hit Control-Shift-Z to toggle off and then back on, off and on. And aside from, you know, you can see it's having some effect on the background noise, but you have, for example, this star here becomes more defined. And you have some structure here, like a little bit of a tendon in the nebula that kind of comes out a little bit. So you can kind of see this is the effect on your image. But de-ringing itself, just the global settings, aren't enough, because what happens is when you have a really bright star like this, it's not going to be enough. So what we're going to do is we're going to build a star mask that's just going to protect the brighter stars. So you go to Process, Mask Generation, and Star Mask. And you can try off leaving these default and see what comes out. And so now we have this. You can kind of hover it over here and see what it's chosen to protect. You can see that, you know, we've got a fair number of stars here, but the really big bright one hasn't really shown up very well. So what we're going to do is we're going to make sure that we increase the scale here. I guess I'll leave that open just so we can see. And for small scale here, you know, you don't really need this kind of protection. Our smaller stars in this image are good enough to be covered by the global dark and global bright, so we'll turn that down. And we'll try again. And here we can see now this star is well protected. By contrast, you can see, you know, the brighter stars here have been blown up a little bit, and so that's good. So we'll close that, close this. We'll rename this here, just Star Mask 1's not very informative, so this can be Star Mask Deconvolution. And we'll just minimize it and stick it up there. And so that's where this goes under local de-ringing. local support. It's our star mask for deconvolution. And this gives a little bit of a extra punch to the areas that are inside our star mask to protect them from the effects of deconvolution. And that's fine, because deconvolution is I mean, you're worried about your nebula or your galaxy, not your stars. The last thing we want to do here, I'm going to delete this preview here. The last thing that we want to do is we want to mask the image. So you saw, in the preview that the background noise was very responsive to deconvolution, but we know that we don't actually care about recovering any information there, and in fact there's probably no information to recover there. We're just seeing strange artifacts because it's very noisy. What I like to do is I just make a clone of the image, remove the screen stretch. So we'll open up screen stretch, and we'll open up the histogram transformation. And what we'll do is we will screen stretch this, Control A, and we'll take the triangle here and we'll drag it onto the bottom here of the histogram transformation. And now we see the histogram is showing us the stretch that would have to occur in order to get the results we see from the screen stretch. So, if I take off the screen stretch and I apply it, boom, looks the same. Now what I'm actually going to do, and that's fine, by the way, that's fine. But what I'm actually going to do here is I'm going to open up the real-time preview. I'm going to zoom in a bit, and I am going to move this up more. So remember, this is a mask, and we don't really need the background to be involved in the deconvolution here. We just want the nebula, the brightest parts here. So I'm going to keep that. Say OK, and here's my mask. And now I'm going to say deconvolution mask with a capital M. And drag it over here to apply it. Then we can minimize that as well. Now we're ready to test out the deconvolution tool. So we'll make a little preview. This is a very CPU intensive situation that we're about to get into. So you don't want to start testing it on the whole image. You want to make a preview. Now, deconvolution is going to rely on some of the information in the image. And so if you make a really small preview like that to save on CPU time, and you go over some interesting feature so you can see it respond, it's not going to be very indicative of how deconvolution responds to your entire image. So instead, I'm going to define a preview, in this case I'm lucky, about that size, and lucky in this case because that actually just covers the object I'm interested in. And that's what I'm going to look at with deconvolution. So I'm just going to leave it actually fully cropped here. And I'm going to bring up the screen transfer function, and I'm going to stretch and just kind of do that a little bit, because as much as we want to make sure that the background noise isn't getting really ugly, we're really here to see what happens to these tendrils inside M1. So we'll put that over there. And now I'm actually going to start the iterations out at 50. I usually do about 100. I don't really think there's any point in doing like 200 or anything like that. 100 is a little excessive, maybe 80. But 50 is like bare minimum that you want to be dealing with. And so I'm just going to put this here. As you can see, this takes a little while. And now this looks very different. So again, off, on, off, on. So you can see a few things. First of all, it's really cool that these tendrils are becoming more pronounced, but they're a little don't know a good word for it. Here it looks more like there's white dots coming out rather than a nice stretchy thing. And here it's a little bit too snake-like. These don't, they're nice tendrils, but it looks like some very clear processing has happened. Further, some of these stars here you can see have now dark rings, and we don't like that either. So this is where you play with these things. Now if you get dark rings around your stars, you need to increase the global dark by a little bit, and then see what happens again. So now off, on, you can see the ringing is still there. It's not so bad, but it's still there. We don't like it, so we'll up it a little more. And always play with the global dark first, get it to something you like, and then we'll worry about these weird snake effects and the global bright. If you see some of these messages, don't worry about it. So now you can see, our star sizes appear to shrink, but we don't get these dark rings around them as much. I'm just going to up that a little more, but I don't need to check it again. So now, we want to keep this kind of definition that we have happening here with the inside structure, but we just kind of want to ease off on the weird effect happening there. So global bright, now global bright is very sensitive, so we're going to do 005 here and see what happens. So now you can see, it's not as harsh. If I undo and redo, we still get some of that definition going on here. We still get it going on here. We still get it all over the nebula. But we don't have that kind of really white jumping out at you. That's actually a pretty good level, so I'm going to keep it at that. So, this is kind of why some people will look at deconvolution and say it's sharpening. We're not really sharpening. If we were sharpening, what would happen is this rectangular structure here would become more rectangular. The transition from the whiteness here to the darkness here would become more dramatic, but it wouldn't recover interior resolution. Deconvolution doesn't make this transition any more dramatic, but it recovers some of that interior resolution here. And so when you go on after deconvolution now and you sharpen, you have this inside rectangle inside this brighter, this darker one, and then flanked by these dark spots. And so sharpening after deconvolution will sharpen finer features, whereas deconvolution doesn't sharpen, and sharpen doesn't recover resolution. Of course, even at further scales, you can see the difference here. So now what we have to do is we actually up the iterations from 50 to 100, and we'll see that our settings are no longer perfect. So here we are. Very little difference, but now we've got these dark circles again, and you're starting to see the spottiness here show up, which we don't like. So that's an easy fix. It's a smaller tweak now. We know which direction. We got a sense for the type of size we want to see, and we apply one more time. So now you can see we have this nice difference happening here. Go out to here, you get this nice difference again too. And so now what we want to do is we want to go back to our main image, and we want to apply it to the whole thing. Now I'm going to let this run for a second just so you can see. I'm running a i7 4770K, and this is the speed that my processor does this on a regular DSLR image out of a Canon 600D. So it takes quite some time. You need some patience here. I also just want to go over a couple things. This wavelet regularization, you don't really ever need to change. You don't need to play with. Why it's there is because under algorithm, you have a couple algorithms. You'll see some have the name regularized in front of them, some don't. And this is only active under regularized algorithms. And all regularized really means is you have some data, in this case your PSF up here, and what it does is, if the PSF were a perfect representation of every single star everywhere in the image, then you wouldn't need regularization, because when you apply deconvolution, everything would be amazing. But in reality, the PSF does differ a little bit from parts of the image, and so without regularization, what you end up with is nice effect where it matches well, and ugly effects where it doesn't match well. So regularization is the process by which data is added. In this case, it looks at the overall image, which is why the preview size you use is important, in order to try to find a median PSF, an average PSF, one that is more applicable generally everywhere rather than great in some places and not so much in others. So you stick with the regularized sides of things, and you can test it out yourself, but you'll find that the wavelets are really useful to have. By default you have 2 that are on, and if you decrease that, you'll actually notice a degradation of the deconvolution effect, if you increase it, maybe in some very fine data you'll see an improvement with 3 wavelets. Most of the time you won't see any difference, and I've never seen a data set that's benefited from having 4 or 5 wavelet layers open. So you can just leave that default and just stick with the regularized Richardson-Lucy algorithm. And you can ignore dynamic range correction. If you wanted to play with dynamic range, you use tools like HDR multiscale transform or local histogram equalization. Alright, now let's have a look. First of all, if we undo and redo at the scale, it doesn't really look like anything because of the screen transfer function. So let's, do a little bit of that. Now, if you undo and redo, even at this scale, you can see, without width, without width. Looks a lot better. And of course, if we go into our full area here and we undo and redo, it's quite a dramatic difference. Now, of course, there is a little bit of a difference between what you see here and what we saw in the preview, and that can't be helped. The larger the region you define into your preview, the more you're going to get what you see. I'm okay with this. You could up the global bright a little bit, tiny bit more here. Because of course any little changes you make here become pronounced later on in the process. You don't want to overdo it this early on. So this is a little bit overdone. I might have pushed the global dark to 0.13 and the global bright to 0.95, but it's not worth really doing it again. And so that's it. You can close this, you get rid of the preview and the mask and all this stuff. Keep all this open. You shouldn't delete any of your information. And now you would move on to noise reduction and other things. And the reason why you would try and do deconvolution as soon as possible is because, again, here was the PSF from the image as it came off the camera after stacking, of course. But noise reduction, as much as it tries to leave the high signal to noise areas alone when you do masking and such, it does start to change things down here. And the deconvolution routines are best when they are taking something that is a blurred PSF and turning it into what should be a good PSF. Once you start altering the PSF with noise reduction tools, one PSF is not necessarily the same as the other. So it's always best to do deconvolution almost immediately. And so that's it. That's deconvolution.